Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I am studying in third semester CSE AI and ML, that is Computer Science and Engineering, with the specification of Artificial Intelligence and Machine Learning, Institute of Aeronautical Engineering. In this complex engineering problem (CEP) of the subject of operating systems (OS), the topic I am going to explain is priority inversion handling with semaphores. First of all, let's go through the contents. In the first place, I'm going to introduce the topic of priority inversion. Next, I'll explain how semaphores cause priority inversion. Next, we'll go through a real-world impact, NASA Pathfinder incident. There is an incident, we'll be talking about it. Next, we'll discuss about types of priority inversion. Next, we'll go through priority inheritance protocol, priority ceiling protocol. Next, semaphore types and their role. And after that, detecting and diagnosing priority inversion, and after that, finally, I'll be going to conclude the topic. So first of all, let's go through the introduction. Priority inversion occurs when a high priority task is blocked whilst waiting for resource waiting for a resource held by a low priority task. This unexpected situation inverts the intended priority order, contradicting the fundamental principles of priority-based scheduling. This phenomenon is particularly common in preemptive scheduling systems that use semaphores for resource synchronization, potentially causing severe timid violations in real-time systems. Now let's discuss about how semaphores cause priority inversion. Semaphores provide synchronization through wait P and signal B operations, but they can inadvertently create priority inversion scenarios. For example, we can take four scenarios. Low priority acquisition. A low priority task acquires a semaphore protecting a critical shared resource. A high priority blocking. A high priority task requests the same semaphore and becomes blocked, waiting for release. Medium priority preemption. Medium priority tasks preempt the lower priority tasks, preventing semaphore release. Unbounded delay. The high priority task experiences an unpredictable delay, a lot of such delays, violating real-time constraints. Now, let's go through a real-world impact. There is an incident, NASA Pathfinder incident. In 1997, Mars Pathfinder mission experienced repeated software resets caused by priority inversion. A low priority task, meteorological data task held a resource required by a high priority information bus task. Medium priority communication tasks repeatedly preempted the low priority task, creating unbounded priority inversion. This incident highlighted the critical importance of priority inversion handling in real-time operating systems, particularly for mission-critical applications. Such types of priority inversions exist in two types: bounded priority inversion. The delay duration is predictable and limited to the resource holding time plus medium priority task execution time. Whilst undesirable, bounded inversion can be analyzed and accommodated in system design. Unbounded priority inversion. The delay is unpredictable and potentially indefinite due to continued preemption by medium priority tasks. This represents a severe threat to real-time guarantees and system reliability. Now let's go through Priority Inheritance Protocol. The Priority Inheritance Protocol gives a dynamic solution by temporarily elevating the priority of the lower priority tasks, holding the semaphore to match the highest priority waiting task. There are four key benefits for this. This PIP ensures resource holding task that runs without preemption. It prevents unbounded priority inversion efficiently. It reduces blocking time for high priority tasks. It automatically reverts after semaphore release. It reverts priority after semaphore release. Now let's go through Priority Ceiling Protocol (PCP). It is a more proactive approach that assigns each semaphore a priority ceiling equal to the highest priority of any task that may block it. There are three types of it. There are three main categories we must discuss in PCP. First, prevention mechanism. A task can only lock a semaphore if its priority exceeds the current system ceiling, preventing lower priority tasks from causing inversion. Deadlock avoidance. The protocol inherently prevents deadlocks by ensuring a strict locking order based on priority ceilings. Bounded blocking guarantees it guarantees that priority inversion duration is limited and predictable, enabling schedulability analysis. Now let's discuss about semaphore types and their role. There are two types of semaphores. Binary semaphore, it is also known as a mutex. It is used for mutual exclusion with single ownership. Tracks owner it tracks ownership to avoid deadlocks and directly supports priority inheritance mechanisms. It now counting semaphore, a second type. It manages multiple resource instances. It handles priority inversion, and this handling process of priority inversion is more complex due to multiple potential owners and resource allocation patterns. The best practice we can use mutexes are strongly preferred over counting semaphores for practical critical sources for protecting critical sources as they provide superior priority, very utmost superior priority inversion handling capabilities. Hence, these are semaphore types and their role. Now let's discuss about detecting and diagnosing priority inversion. Sophisticated diagnostic tools like Tracializer provide essential visibility into task scheduling behavior and semaphore blocking patterns within real-time operating systems. There are four major detection capabilities to discuss. The first capability is of visualizing task scheduling timelines and transitions, then identification of watchdog timer resets caused by inversion, and profile semaphore wait times, the profiling process of semaphore wait times and blocking chains. And lastly, validation mitigation strategy effectiveness. Early detection through profiling helps identify inversion patterns before they cause system failures. Now finally let's conclude the topic. Conclusion. Designing for priority inversion handling. Hence, proper design and implementation of priority inversion handling ensures system reliability, responsiveness, and deadline adherence in mission critical applications. There are four major aspects we should finally discuss. Critical, a critical challenge. Priority inversion represents a fundamental challenge in real-time and priority-based operating systems that can cause severe timing violations. Protocol solutions. We have to implement priority inheritance or ceiling protocols with semaphores to prevent unbounded delays and ensure predictable behavior. Design choices. The design choices. We have to prefer mutexes over counting semaphores for critical sections, as they provide superior ownerships, ownership to tracking and priority handling. And finally, proactive monitoring. We have to employ diagnostic and profiling tools to detect and resolve the priority inversion early in the development cycle. And finally, I would like to sincerely thank the respected professor for giving me this wonderful opportunity to speak upon this wonderful topic. Thank you.